Welcome to the module of vibration of single degree of freedom systems. So, the outline of this module is I will introduce you to this module, and then vibration of buildings, single degree of freedom systems, external force, and will formulate the dynamic equilibrium equation using Newton's second law of motion and also using force approach. Introduction. So, usually vibration is oscillatory. So, oscillatory means any to and fro motion. So, that simple harmonic motion is called oscillatory motion, and its effects are very common in our daily life. So, for example, not only us, universe around us is governed by periodic motion, that is day and night. So, this cyclic motion is continuously taking place. You see any phenomenon in that oscillatory motion is already present in. So, why we need to study this vibration, or why its study is important? Its study is important because of the construction these days is going towards tall structures. So, that is because of the technology development. So, these tall structures are susceptible for vibrations from earthquakes or as well as wind, and then machines which are installed on floors of the building, and these are the forces which might come onto the structure. Now, if you take a typical building which is subjected to earthquake ground motion, so you can see here this one, so U double dot G. So, we call U as displacement, U dot, which is a derivative of displacement, as we call it as velocity, and U double dot is acceleration of the structure, and when we use suffix G, we call that as acceleration of the ground. So, this building is subjected to earthquake ground shaking. So, a multi-story building. So, this multi-story building can be idealized as many degrees of freedom. So, like mass 1, mass 2, mass 3, mass 4 and mass 5. So, 5 degrees of freedom system, like supported by columns which are having stiffness from K1 up to K5. So, this is a complex system. So, before understanding the complex dynamic behavior of multi-degree of freedom system, let us discuss single degree of freedom system. So, where one story structure is a typical example of that. So, as you can see here, like this single story building, or say like single story structure, where slab is supported by 4 columns. So, slab and 4 columns. So, column 1, column 2, column 3 and column 4 columns are there. So, this structure can be given initial vibration or initial displacement or initial velocity. So, set the oscillation. So, it will undergo free vibration if we just give initial condition or initial displacement or initial velocity and leave it. So, give initial conditions, that is either velocity or displacement, to initiate vibration, and the structure is set to undergo free vibration when it is disturbed from its static equilibrium position. So, this idealized system can be represented by mass and stiffness, mass and spring system. Now, initial displacement, initial velocity, or both. So, if we give initial displacement here, as you can see in the horizontal axis, this is time scale, and we are giving at time t is equal to 0 some initial displacement. So, which we are calling it as initial displacement here. U at time t is equal to 0 is not equal to 0. So, that means some non-zero displacement is given, and u dot, which is velocity at the initial time, that time t is equal to 0, is 0. So, initial displacement is given and the system oscillates according to its frequency around time scale. And then when it comes to initial velocity, here initial displacement is 0 and we are giving initial velocity. Initial velocity means, you can see here the tangent at this point at the time t is equal to 0 is not 90 degrees. So, it is, and you can clearly see here that displacement is 0 at this point. So, in the first case we are giving initial displacement, but initial velocity is 0. In second case, initial velocity is there, but initial displacement is 0. Then third case can be like both initial displacement has some value from here to here, and then initial velocity also has some value. So, initial displacement, initial velocity and initial velocity along with initial displacement both. So let's look at how the external force is applied on the structure. As you can see, the system or the single degree of freedom system can be represented in the form of, say, slab, and this one and this one you can call it as columns, and any system will have internal friction. So that means free vibration is usually not always continuous. So if you set free vibration, after some time vibration dies out. That is due to many reasons. One important reason is internal friction between the material of the column. So that will reduce the energy of vibration. So we will discuss this damping phenomenon in detail, but to start with, we indicate damping as a dashpot. Damping as dashpot. So mass of the structure and then resistance comes by column, which we are representing as stiffness, and damping reduces the energy in vibration, and this P is the external force which is being applied. Now this P as external force, this is not a static force. A static force is always constant, whereas a dynamic force always changes its value according to time. Now we derive dynamic equilibrium equation using Newton's second law. So if we write, say, cut the system and write free body diagram, this external force is applied here, and then inertia force is opposing the motion, and then this is stiffness force, by which is coming from k by 2, and then this is damping force. So now if we write equation of equilibrium, so this external force, stiffness force, damping force is equal to inertia force. If you look at the nature of the arrows, then mu double dot, then damping force, then stiffness force, which is equal to the external force. So the same thing can be written like inertia force, damping force, stiffness force, which is elastic resisting force, applied force. So the same thing if we write in inelastic systems, which will become like this. Here resisting force is not only function of displacement, but also it is function of velocity. Now the same dynamic equilibrium equation, if we get it through force approach, how does it look like? So this is single degree of freedom system, mass is there, springs are there, and then damping is there, and external forces applied on the system. Now if we idealize this system as mass spring damper system. So mass spring damper system means, say if I am vibrating the structure, if I give initial displacement or initial velocity to the structure, this structure vibrates. So that means elastic force, that is resisting elements which are columns are trying to pull the mass back. So that is represented by the spring. So spring is having stiffness, and then after some time, after few cycles, it will come to rest. So that is represented by a damping present in the structure, and mass when it comes back, it overshoots. So that means mass is oscillating to and fro at the mean position, and then this is done by inertia force. So in this one, if I am idealizing it as mass spring a damper system and give initial displacement to this one, so this will set to and fro motion. Now for writing dynamic equilibrium equation, so what I am doing is I am drawing a free body diagram here. So this free body diagram is mass, that inertia force because of the mass is in the direction opposite to the application of the force, that you can see in terms of mu double dot. So we call this as inertia force, and then if I apply this force in the forward direction, then the resistance of the spring comes in the backward direction. So you can see this one k into u, and then damping force also in the form of k u dot, and then external force in the towards right direction. Now if we write this equilibrium equation, so we get mu double dot and plus cu dot plus ku. All these things are u dot and u double dot are respectively displacement of the system, velocity of the system, and acceleration of the system measured at the center of mass of the structure. Okay, all these things, they are respectively displacement, velocity, and acceleration. So this first term we call it as inertia force, second term we call it as damping force, and third term we call it as elastic force. So all these forces added together will become equal to externally applied force. So this equation can be understood as appearing from the D'Alembert's principle, which says that moving mass generates inertia force opposing the motion. So as you can see here, mass is moving in the forward direction, inertia force is generated in the backward direction. Now this vibration of the system, let me write mu double dot plus cu dot plus ku is equal to p of t. So in this we can understand this equation of motion as a general equation of motion, but from this various conditions can be understood. So that are free vibrations. So free vibrations means when external force is not acting on the system, we call it as free vibration. So when external force is not acting, how the vibration is taking place? So vibrations take place because of the initial disturbance to the system. So initial disturbance to the system can be something like this. So if I give initial displacement, it sets to oscillation, and initial velocity means I am giving impulse to this one, initial velocity and this initial velocity, or I pull this one and hit it, initial displacement along with initial velocity. So this is free vibration. And then forced vibration means like when externally applied force is there, which is dynamic in nature, so that is forced vibration. And the another case is undamped free vibration, damped free vibration, and then undamped forced vibration, damped forced vibration. So these are the four cases, so which we will discuss in subsequent modules. So in summary, what we have studied in this module is vibrations of the building, and what is a single degree of freedom system, how external force is applied, and how to formulate dynamic equilibrium equation. We formulated in two methods. One is using Newton's second law of motion, and second one is force approach. That is force approach is D'Alembert's principle. Thank you.